Welcome to Introductory Chemistry with Dr. H. This is a video about the structure of matter. Particularly, I'm going to talk about atoms, elements, compounds, and mixtures. And then we're going to dig into atomic structure. We'll talk about the subatomic particles, the electrons, protons, and neutrons. And then we'll talk about this term called isotopes as it relates to elements. Finally, we'll talk about atomic symbols and how we use atomic symbols to represent elements. So an atom is the basic unit of an element or of matter. All matter is made up of atoms. Atoms are these tiny, tiny things. If you think about the diameter of an atom, it's about 200 picometers across, which is 200 times 10 to the minus 12 meters, much, much smaller than we can see. If you have many of the same type of atom, we call that an element. So an element has properties. So some elements that you might be familiar with are things like helium. So helium, as we know it, is a gas made up of helium atoms, and they are less dense than the air, the nitrogen in the air, and so if you fill a balloon with helium, it floats. Another element you might be familiar with is mercury. So mercury is that silvery liquid that we used to find in thermometers. Mercury, the element, is made up of mercury atoms. That's what makes it an element. It's all of the same atom type. And a solid that you might be familiar with is diamond. So diamond is carbon atoms all bound together tightly in a lattice. So elements are collections of the same type of atom, and they can occur in nature in many different forms. Here I've given you a gas, a liquid, and a solid form that you might be familiar with. Compounds, on the other hand, are collections of atoms. So a compound that I'm sure you're familiar with is water, particularly a substance that's composed of multiple types of atoms that are associated in a fixed proportion is what we call a compound. So for example, water has 2 hydrogen atoms and an oxygen atom bound covalently together. So if you have 1 water molecule, the ratio is 2 hydrogens to 1 oxygen. If you have a gallon of water or an ocean of water, the ratio of oxygen and hydrogen is still the same. For every 2 hydrogens you find in water, there's 1 oxygen. Each water molecule is bound together in its own little covalent package, and it's about 270 picometers across, so slightly bigger than an individual atom would be. We know that water can take on different forms. So for example, when you heat up water, you make steam. So in steam, the water molecules are relatively far apart from each other, even further apart than in this picture, but importantly, they're not really interacting much with each other. In steam, the water molecules remain water. They remain those 3 atoms bound together, and occasionally they might collide with another water molecule, but they remain discrete entities with 2 hydrogen and 1 oxygen. That's true also if we cool that steam down and we make water. Water is the liquid form of this element or of this compound, and in water there are actually interactions between water molecules because they're colliding quite frequently and they're holding each other together. That's what makes them condense into water. But each of those water molecules within the water remains a discrete 3-atom compound, right? So those molecules are floating around. They can move relative to one another, but they keep their identity as water molecules. So if you cool water down, we all know that it will form ice. So ice is a 3rd phase of water. In ice, there are still discrete water molecules, but those discrete water molecules are now fixed into a lattice, a regular lattice. And we recognize ice when we see it. It's the hard form of water. It's the solid form of water. It's cold. It's the cold form of water. So that's an example of a compound that you're familiar with. So a mixture is anytime you have 2 or more substances that come together. So for example, if I had helium gas and I pumped that into some container, and then I pumped some steam in, some water in its gaseous form, what would be inside that container would be discrete helium atoms and discrete water molecules, but they're intermixed. So we call those things mixtures. So whenever you have 2 or more substances, that could be an element with an element, it could be many different elements mixed together. All the elements retain their individual characteristics in that mixture, but they're all together. Here we have a compound in an atom or a compound in an element, helium and water. Those are also mixtures. You certainly can have mixtures of compounds where there are many different compound types all mixed together. But in principle, you can separate them back and they all sort of remain, have their original identity once you separate them apart. So that's what a mixture is. Let's dig into atomic structure. What makes up those individual atoms that are part of elements and are part of compounds? And we're going to use the example of the carbon atom as our first example. So a carbon atom has a diameter of 140 picometers. That diameter is actually defined by the space that's almost entirely filled by electrons. So if you zoom in on a carbon atom, what you would find is there are 6 electrons whizzing around in a sphere of electron density, roughly a sphere of electron density. And those 6 electrons really are what fill that entire volume of the carbon atom. Each electron has a -1 charge. A -1 charge has a charge of about minus 1.60 times 10 to the minus 19th coulomb. So it's a tiny, tiny charge. And those electrons whiz around so fast that if you put your finger anywhere in that sphere, you would collide with one because they're all moving around, filling that shape. We're going to learn later specifically where in space those electrons are. But for now, let's just imagine the atom as a sphere of electron density. And all of those electrons have a negative charge. That negative charge is counterbalanced by protons, which are in the nucleus. The nucleus is super tiny. So if we zoom in again to a degree where we could see something that is 0.005 picometers, that's 0.005 times 10 to the minus 12 meters. Tiny, tiny center is called the nucleus. And within that nucleus are the positive charges, the protons that counterbalance the charge on the electrons. The entire atom is neutral. So protons, as it turns out, are much bigger than electrons. Their mass is 1.67 times 10 to the minus 24th, whereas the mass of an electron is 9.1 times 10 to the minus 28th. So protons are much, much larger. They have the opposite charge of an electron, so a +1 charge or a +1.6 times 10 to the minus 19th coulomb charge. And together the protons and the electrons form a charge-neutral atom. So the number of protons in the nucleus is what defines the element. So this is carbon. So the element carbon has 6 protons in the nucleus and thus 6 electrons counterbalancing that charge. And interestingly, in the nucleus, we also find a species that has a neutral charge called a neutron. Neutrons have almost the same mass as a proton, so 1.67 times 10 to the minus 24th. It's actually slightly larger than the mass of a proton. And they also reside in that tiny, tiny nucleus in the middle of the atom. And so if we kind of imagine what a carbon nucleus would look like, you'd have the protons that I've labeled kind of in purple here with orange neutrons. That's sort of the most common way we find carbon in nature. Okay, let's talk about carbon just a little bit longer. So here's again our picture of carbon. And what we just talked about was that in nature, all carbon atoms, for example, have 6 electrons and 6 protons. That's what makes it carbon. And most of the time in nature, there are 6 neutrons also in the nucleus. That's what we have illustrated in this nucleus here. About 99% of carbon that you find in nature has that combination of subatomic particles. However, there are other isotopes of carbon that also exist. And the next most common isotope is carbon-13. It's found in nature in about 1% of the time. So carbon-13 simply means that the sum total of subatomic particles in the nucleus is 13. We know that to be carbon, you have to have 6 protons, so that means there must be 7 neutrons in that nucleus. So carbon-13 has 6 electrons and 6 protons. It's charge balanced, and it's carbon, so it must have 6 protons. And then it must have 7 neutrons in the nucleus, right? So if I wanted to correct this picture to show what a carbon-13 nucleus would look like, I would have to add another neutron to that picture, so a total of 7. It looks like it already had 7, so I need to erase that one. So I'm counting 7 orange dots on that. So that is what we would call carbon-13. That is the isotope of carbon that is less abundant than carbon-12. And those are the 2 most abundant isotopes. They make up almost 100% of the carbon that you find in nature. So that word isotope just simply distinguishes the number of neutrons that are in the nucleus of a particular atom. Okay, so let's just review this atomic symbol because I've been using it a little bit here in context, but I want to make sure you understand. We typically symbolize atoms using an atomic symbol. And in the atomic symbol, there are sort of 3 characters that are important. X is the element. The element is defined by the number of protons that are in the nucleus. The number of protons that are in the nucleus, that is called the atomic number, and it's indicated by that Z. So Z in this nomenclature is the atomic number, or the number of protons in the nucleus, which we know on the neutral atom also equals the number of electrons that are there, if it's a neutral atom. The mass number is the sum total of subatomic particles in the nucleus, so that's the sum of the protons and the neutrons. And interestingly, we call that number A. And the way we symbolize that particular element, that particular isotope of an element, is like this, where X is the atomic symbol coming off of the periodic table, Z is the atomic number, and A is the mass number. So hydrogen is an interesting case. It has 3 isotopes that occur in nature that we can find. The most abundant one is illustrated here. It's got the atom itself is tiny. It is 50 picometers in diameter. If we zoom in on that, what we would see, if we looked really closely, a tiny, tiny nucleus, and there's just 1 electron floating around in most of that volume. That means in the nucleus, there's only 1 proton, and in fact, there are no neutrons in the most common isotope of hydrogen. So in the nucleus we have atomic number 1, and in the nucleus there are no neutrons, so the mass number is also 1. So we would symbolize it that way. We have 1 electron, 1 proton, and 0 neutrons in hydrogen 1. The next most abundant isotope, and by the way, hydrogen 1 is greater than 99.99% of the hydrogen that you find in nature. The next most abundant isotope is what we call hydrogen 2, or deuterium. That's another word for hydrogen 2, and it has a mass number of 2. In order to be hydrogen, it has to have just 1 proton in the nucleus, so we call that one deuterium, and so it has 1 electron, 1 proton, and 1 neutron. So if we want to update the structure of this nucleus to be for deuterium, or hydrogen 2, we would have to add a neutron in that nucleus. So that's what the neutron would look like. I can even add a little dot there to show that in the nucleus of the zoomed in atom. The third isotope, unsurprisingly, is what we call tritium, or hydrogen 3. So hydrogen 3 has a mass number of 3. It has an atomic number of 1. It's still hydrogen. And so it has to have 1 electron, 1 proton, and now it has 2 neutrons. There are only traces of tritium in nature. In fact, it decays. It's a radioactive element. It decays down and becomes deuterium when it loses one of the neutrons in the nucleus. So if we wanted to update the nucleus again to show what the tritium nucleus looks like, so this would now be the tritium nucleus, and I would have to add another little dot over there. So now we've sort of used an atomic symbol, including the atomic number, the mass number, and the elemental symbol to show what atom we're talking about, right? That's how we communicate what atom we're talking about. All right, let's do one more example and wrap this up. Let's do a bigger element. Let's talk about bromine. Bromine, I've already sort of written their symbols down here. Bromine has 35 protons in its nucleus, and thus 35 electrons whizzing around most of its volume. So I'm not going to draw 35 dots in there, but you can imagine 35 electrons floating around, 35 protons in the nucleus. And as it turns out, what we observe in nature, there are 2 common isotopes. And what's interesting about it is they're found in almost equal proportion. 50.7% of the bromine nuclei that you find in nature have 44 neutrons, and so a mass number of 79. That's the most abundant isotope, but it's only the most abundant by a little bit. 50.7% of that isotope is the common one. And so I think actually I have to erase one of these little neutrons. That would be your bromine 79. The other most common isotope, the one that's present in about 49.3%, so almost the rest that you find in nature, has 46 neutrons in the nucleus, 46. And so, you know, if I wanted to update the nucleus here, I would have to add back that neutron, and I'd have to add one more tiny, tiny dot to the nucleus in that picture. So there's just another example of how we would represent an element, and particularly the isotope of an element, using our atomic symbols. I hope you found this video useful.